Good evening, good morning, or wherever you are. My name is Nico, and I'm Head of Solutions Architecture at Bavarica. And in this webinar, I'd like to talk about monitoring large-scale Apache Flink applications. So let's get started. As the original creators of Apache Flink, we as Bavarica are often asked for best practices around monitoring Flink applications, and people would like to know which metrics they should focus on. Here in this presentation, I'd like to share our experiences, and we'll look at understanding the concepts, like how Flink's metric system works, what monitoring is, and then eventually get to look at the metrics, the key metrics that you can use to continuously monitor your Flink applications and do troubleshooting with it. And we'll look at a few details along the way. First things first, what is monitoring? So Technopedia defines it as application monitoring is a process that ensures that a software application processes and performs in an expected manner and scope. This technique routinely identifies, measures, and evaluates the performance of an application and provides the means to isolate and rectify any abnormalities or shortcomings. But what does this make special? Where is Flink special in this regard? I mean, you could say monitoring is difficult in general, or people struggle with it, but there are a few specialties that when it comes to monitoring Flink application. And first, Flink is a distributed stream processing framework. And this adds more complexity because jobs may run, for example, at a very high parallelism. They could also run on multiple machines. That usually goes together. They run at a vast set of different environments. People configure their machines, their software in so many different ways. And then there are also a lot of abstraction layers, typically between the user code and the systems. Like think of virtualization, or when you run your applications in Kubernetes, on the cloud or on premise. So there are a lot of abstractions in between. And then Flink applications can also be run in different modes. Like you can run an application mode per job and session modes, and you can configure Flink also in any way possible. Flink is also running arbitrary user code. So it's your logic that you're running. It's custom business logic, and that varies in behavior quite a lot. Like your code is probably so much different from someone else's code, and there's so many different use cases that Flink supports. So this, plus especially for large-scale systems, monitoring becomes a challenge because it's so complex based on those settings. And we're trying to demystify a few things and try to help you get the best practices of monitoring your large-scale applications and reducing the complexity. So first, let's think about what tools we can use. Like common tools that you can use for large-scale, but also not so large-scale applications. So I don't want to make this exclusively for large-scale applications. This is technically for every Flink application that you want to monitor, which you put into production and then want to see and verify its behavior. So first of all, we could use log files. Logging. Flink logs a lot of things, and that is typical at info level, where you see what is happening underneath. While this is useful for debugging failures, it's not really suitable for large-scale monitoring because it's just too much data, and it's difficult to set up alerting based on log files. Even if you put this into other logging systems like Elasticsearch. So in that case, why not use the system level metrics? So wherever we deploy our Flink applications to, we will have metrics about what's going on the system. How's the CPU load? What's the memory that is being used? Disk I/O, etc., etc. They help you understand what your application is doing at a, let's say, coarse-grained level, and help you to understand what is going on. It doesn't, however, not give you too many insights into the application layer. So the next thing you want to look at is the metrics that come with Flink, so built-in metrics. They give you much more detail about what is happening inside Flink. However, they lack the insight into your user code. So then you might want to add your custom metrics. Sure, they are the ideal extension to the built-in metrics and also to the system level metrics. All of them together usually form a pretty well dashboard or insight into what is going on the whole application. And finally, you can also use profilers. They help you very well if you do troubleshooting or performance tuning, because they give you a real insight into where time is spent and other things, like also where you're locked at. But this level of detail is just too much for monitoring, for continuous monitoring and alerting. So it's a useful tool, not just for monitoring, but just not for monitoring. So let's first have a look at how Flink is making its metrics available and which metrics types it supports and how they can be used. So first of all, metrics are objects that measure something. Obviously, they are identified by some identifier, and then they have some value, some measurement that they collect. So that measurement in Flink can be one of four types. It can be a counter, is things like, for example, how many records has this task seen? So number of records in. Where you have counters, and you also have time, and then you can measure rates, and that's a meter. A meter is, or are things like number of records per second, like a number of records in per second, and a lot of other built-in metrics, or your own. Then Flink also offers histograms, and with those you can kind of get a distribution, like for example the latency, like where's the 99th percentile of your latency, or your median, or other values in between. So histograms give you a lot more detail on the distribution of your individual values. And then finally, the fourth type is a gauge, and that one just returns an arbitrary value. So it's a single value, like the Flink job has been up for 35 minutes. And in the next minute, it has been up for 36 minutes. And those are the four metric types that Flink comes with, that Flink supports. Now, metrics inside of Flink are put into a hierarchy of metric groups or scopes. So each metric is scoped to specific context within the Flink runtime. And that creates metrics with identifiers that start with a system scope, then an optional user scope, and eventually you will have your metric names. So in the end, you build up a tree of you're starting at let's say task manager, and then you look at a specific job, and then you look at specific task in a job, and so on. So typical system scopes are, well, job manager for the job manager, obviously. Then inside the job manager, you can scope further by the job that is running on the job manager. On the task manager side, you also have general task manager metrics. Then you have metrics that are tied to a specific job that is running at a task manager. And then you can scope further to tasks and operators. The difference between task and operator is, well, one task can host multiple operators if there is an operator chain in there. And some of the metrics make only sense as a whole task metric. It's things like network communication, because they occur at the start of a task, so at the input of a task and at the output of a task. And others, like operator metrics, could also be in between, like the current watermark. And they are tracked by individual operators. When you now put these metrics out into, well, your metric system, those scopes and metric names are, those scopes define your metric names, and you can define via scope formats how these metric names are finally, like what the format is of those final metric identifiers. This might help you with certain limitations on metric systems, or they help you put things, well, just put your own names into things. So there are a couple of scope formats that you can configure inside of Flink. I don't really want to go into the details, just so that you know you can configure the actual composition, like what makes the final metrics identifier. Well, now we've looked at metrics, mostly metrics that are built in. It's also actually fairly easy to implement your own metrics, your own custom metrics inside a Flink application. And we'll see one more example at the end of the deck. We'll just start with a very simple one. This one adds a number of records in counter. That's not really too useful because that's already a built-in metric, but it's just here for demonstration purposes. So the thing that you need in order to get started with a custom metric is, well, from the runtime context, you get the scope, so the metric group that this operator of yours is running in. Then you can optionally add your own scopes, or you can just use that as it is, like in this example, and then you decide which metric type you want. In this case, it's a counter, you give it a name, and that's it. And you store it inside your object, and then you can just use it. So in this case, it was a rich map function. So inside your map function, whenever you want, you just increase that counter. For other metric types, functions will be different here, but for a counter, it's an increase, and I think there might also be a decrease. But that's easy to look up in the counter class. So that's a custom metric. Now we've seen built-in metrics. We've seen how to do custom metrics. The only thing that we need to know, one of the next things we need to know, is how can we access metrics. And metrics are exposed by Flink in various ways. One is metrics reporters. So those connect to external metric backends. We'll see a bit more about this on the next couple of slides. Then you can retrieve metrics from Flink's REST API. There are a few endpoints that you can query, and you can get metrics like from checkpoints or from very specific parts of your pipeline. You can also use the web UI, as you see on the screen, and I think most of you probably looked into that one way or another. However, I want to give a friendly advice. Don't really use Flink's web UI as a metrics dashboard. Like whenever you're serious about your application, create a real dashboard in a real metric system. Flink is not aiming to be a metric system. So Flink's web UI is, let's say, rather limited at displaying the metrics. You can't do things like aggregations. You cannot combine different metrics into a single graph and a few other things that a typical metric system has. So if you want to go into monitoring, I recommend that you set up your own metric system, that connect Flink to a metric system and then have a proper dashboard. And while we speak about connecting Flink to a metric system, that is done via metrics reporters. And they exist in many flavors, like there are ones for Prometheus, Ganglia, Graphite, InfluxDB, and more. Like you see some of them on the screen. They're all built in, so you don't really have to do much except for configuring it and tell it how to connect to your own services that provide your metric system. If your metric system is not in here, then it's actually also quite easy to write a metrics reporter. That's not much, or that's not no black magic, actually. And I have a simple example that is here on the screen, and that reports metrics in the log file. Now, that might be useful for debugging, because you can very easily just see the metrics on the log, but it isn't really useful for production environments. Also, while I present the code here, you don't actually need to write this if you want to have metrics in the logs. Flink already has a metrics reporter that is the SLF4J reporter that does exactly that, what the log4j reporter is doing on the screen. So this reporter just keeps track of the metrics it wants to present. So there's a map of your metrics. In this case, we're only looking at counters. And we track the metric to the name of the metric. So whenever a metric is added or removed, we get a callback from Flink in our notify of added or removed metrics. And then in this case, we will just add counters and we will ignore everything else. So it's up to you. It's your implementation of the metrics reporter. In this case, we only want to report counters. You can also only report specific metrics. This might be something that you want to do for having this as a debugging tool. And eventually, if you implement the scheduled interface, then you get an additional callback that is called report. And whenever it's time to report metrics, then you can connect to your external systems. If you don't want to report metrics actively, then what you can do, whenever a metric is added, you just connect it to your external metric system. Like for Prometheus, you connect it to the actual Prometheus implementation. So you make that metric known to the metric system, and the metric system will then take care of reporting. So there are different ways of achieving what you want. And it should satisfy all the needs for different metric systems that there are. All right. Now we pretty much covered the basics of metrics in Flink, like what are the metrics, how are the metrics being used, and how you can connect to external systems. Actually, if you also have a question, like feel free to, well, you can put them into the chat, and you can also use the Q&A part of this webinar, and then we'll try our best to answer those questions either live, or this is where my colleague David will help us out, or we can do that at the end of the session. So the next part I'd like to look into is key metrics for continuous monitoring, and those usually also serve for troubleshooting. So we'll have a look at some of the useful examples, how to monitor your large-scale application, how to set up alerts, or how to use them if you want to know more about what your application is actually doing. So first, let's start with application health. So first of all, is your application running? Well, it's not so difficult to find out which metric to look at for this. There is an uptime metric, which gives you how long the application, how long your current job has been running, and you can also look at the number of restarts. If you plot this like in the dashboard that I'm showing on the slide, then you will see how often your job is restarting, and that is something that you can also put alerts on. So you can, for example, configure an alert, say if you've seen this many restarts in a certain period of time, then trigger someone who's on support and then look at it further. What you can also do is look at the uptime and compare it with the actual time in a certain interval. And then you see, like, this job has been up for 90% of the time or lower. You define the threshold, and then you get alerted by this. While we are looking at restarts, there are a lot of different reasons why a job may restart. In a well-behaved system, well, most of these originate from transient failures, but you want to make sure that these restarts are recovered quickly. And this is what you can track with the restarting time metric. It gives you the time that Flink has spent while restarting. So loading the checkpoint, for example, getting up the additional resources, configuring RocksDB, etc., etc. So everything that is needed during a restart. And you can put up an alert on the restarting time. Like if a restart is taking too long, well, at the moment you can't do much against it, I suppose, but you can give this back to your development teams. You can also give this back to your platform operators, and then you can try to work around it. Especially if you have a latency critical job. Then restarting time means that you're not putting any events on the output. So you might hit your SLA on the latency that you've defined for your job. So you want to monitor this and then eventually do something against it. Here we, by the way, focus on the monitoring side of things. We're not going into too much detail of the how to fix parts, but the first thing before you can fix something is finding out what is wrong and finding out that something is misbehaving. That is even the first thing. All right, so we're at application health. We've seen restarts. The next thing, since failures can happen at any point in time, you want to make sure that you don't have to go back too far. Like Flink's fault tolerance is based on point-in-time snapshots, and those are checkpoints. And whenever you have a failure, you would go back in time to the latest checkpoint and then resume processing from there. While you go back in time, that means you also have to reprocess data from however long you have not done any checkpoint. So what you want is that the last checkpoint is not too long ago. And for this, you can look into checkpointing metrics. Also, one more reason to look into checkpointing metrics, what you usually do is to configure Flink to restart if too many failed, or if Flink had too many failed checkpoints. And you might not want to wait for this, but you might want to track it in advance. So we'll look at things like number of completed checkpoints, number of failed checkpoints, and by also tracking the number of in-progress checkpoints you see whenever Flink attempted a checkpoint or whether it's currently running. So you can plot something like the chart that I've been using here. I have a global counter of how many completed checkpoints. Well, this job didn't behave very well because it didn't have any completed checkpoints. Instead, it had 7 failed checkpoints. Like I tried a couple of times, but it failed. So things you want to get alerted on is if the number of failed checkpoints in a certain interval is above a threshold. Or what you can also do is you can look at the time of the latest completed checkpoint and compare that with the current time. And if it's just too long ago, then you want an alert. Now, unfortunately, this last part is nothing that Flink offers you directly. So there's no metric for time of the latest completed checkpoint. What you can look at, however, is you look at the last, well, you can check Flink's REST API for once, or you can look at the latest value or when the latest change for the number of completed checkpoints was reported and just look at the timestamp there. And then you kind of have an estimate when the latest checkpoint was completed. All right, we're going away a bit from application health, but we will stay with checkpointing. So we're looking at checkpointing, and what you should keep an eye on is checkpointing times. Like this is, well, I'd say, the most prominent thing that fails a checkpoint, because you usually, well, you do have to configure a checkpoint timeout, and you don't want to have an infinite checkpoint timeout. So eventually, if a checkpoint is taking too long, you want to fail and you want to start again, because maybe it's a transient failure, maybe a restart already solves the problem. So there's a checkpoint timeout. You can look at the last checkpoint duration, and from there you see how close you are to the checkpoint timeout. So when I say there's a possible alert on this, you look at the checkpoint duration, whether it's above a certain threshold, or you can also track how far it is from the actual checkpoint timeout and use that as your alert. Then one thing you might also want to look at is how your state size is progressing. One thing you want to be alerted of is a situation where your state, for example, is growing and growing infinitely. That you can track via system level metrics, like you look at the disk, you just see how much data it is using. That's certainly the, let's say, most accurate metric for finding out how large your checkpoint or checkpoint storage is. It is, however, not tracking just one checkpoint, but probably more of them. Flink offers a metric called last checkpoint size, and this is something that you can use. And you can see whether last checkpoint size is growing or is growing above a threshold. You probably did some experiments before you went into production, and you saw roughly how large your application state will become, and then, well, you get an alert if it grows bigger, and then you investigate more. There's, however, one downside to this metric, and this is if you're using incremental checkpoints, which is quite common to use. If you're using RocksDB as a state backend, you can opt in for incremental checkpoints, and then only the data that has changed will actually be written to the checkpoint file system. And only that data size will be reported as the last checkpoint size. So it's not the size of the state, like the complete state inside the checkpoint. The last checkpoint size is just the increment that was sent. Whenever you have to restore, you will have to restore like a full checkpoint and not just the increment. So that's a downside. Flink 115, however, is about to change that behavior. It's still a bit undefined how exactly this is going to happen. In the current state of the master branch, the last checkpoint size just changes semantics. And with the current master branch, it means the actual state size. But this is a backwards incompatible change. So Flink 115 hasn't been released yet. So we'll probably see some changes in there, and you can track it under Flink 25557. All right, enough about the checkpoint size. You can also look at the checkpoint alignment time. I put this with some spacing on the slide because that's technically not much of a metric to continuously monitor, but rather something for troubleshooting. And when you're looking at checkpoint alignments, then maybe you're actually also looking into the Flink UI, into the Flink web UI, because that contains more details on the alignment and where time is actually spent during a checkpoint. So this is more for troubleshooting. Also, well, I say you could put an alert on the last checkpoint duration and that being above the threshold. Well, you can do that. On the other hand, it might not be needed because if you hit the threshold, if you hit your checkpoint timeout too often, then the checkpoint will become a failed checkpoint. And if you're already monitoring failed checkpoints, then that might just be enough to monitor. So monitoring also the last checkpoint duration, that might just give you too many alerts. So maybe it's enough to just look at the actual checkpoint failures. Nonetheless, this is very useful for debugging. Let's move on from checkpointing to latency. The most important part to look at a job, if that job is running event time logic, is are we making progress? This is because event time applications rely on watermarks to continue and advance in event time. And therefore, it's a good idea to monitor the watermark at time-sensitive operators in your job graph, such as process functions or windows, by watching the difference between the current time of the day and the watermark. And that is something that we call the event time lag. If this event time lag is unusually high, then it indicates that either you are processing older events, maybe you had an outage and restarted, so you're going back in time, and therefore the event time lag is high, or something upstream has not sent a watermark for a long time. For example, if a source becomes idle, then you don't get any watermark, and the overall event time is progressing with the minimum of all the input watermarks. And if just one partition or one source is idle, then you wouldn't be able to make progress in your job if you use event time logic. If that is the case, then you have to find a workaround that's usually in code. To get the event time lag from the built-in metrics, what we can do is plot the timestamp of gathering the value of the current output watermark versus the actual value of the current output watermark. And this is what I did in the graph on the right. So I have the current time of when I, in this case Prometheus, received the metric, and I have the metric value, so the watermark's timestamp, and then I can compare those two. Now, this is an estimation, but it's usually good enough. What you can also do is track this at different levels. So what I've done here is I track this per subtask of a specific task. And that can be useful to identify event time skew. So as you see in the graph that I'm showing here, like this red subtask 3, that is a bit further behind at this point in time than the others. So there might be some skew in event time between the different subtasks. What you can also do is just track this by your operators. And instead of plotting the subtasks, you just plot it by operator, and then you see how event time is making progress throughout the different stages of your job graph. And well, you can present this in so many different ways. One part that also got useful for presentation for debugging is to just print the watermark. So here we see the current processing time when the metric was reported versus the actual watermark's time, and then we can look at things in more detail. So a downside of this, plotting the event time metrics reporting time versus the event time metrics. So when I say event time metric, I mean current output watermark versus the current output watermark, is that at least with Prometheus, the timestamp of the reported metrics is only in second accuracy. So if you have very low latency use cases, then this might not be enough. For everything else, it's a really useful estimate that has been working quite well. But if you have low latency use cases, then you might, then you can just use a technique that I will go to here on the next slide. And it's similar to the needs that you have if you have your very own definitions of what latency is. So there's no common definition of latency, because it depends on what you're doing, it depends on what you want to look at. Now, in the previous slide, we looked at the event time lag, so the difference between the processing time and the event time, basically, and that one includes time that is spent in external systems at the source. So if an event was created an hour ago, then put into Kafka, then I read it at some point in time, and then I look at the event time lag, then this includes everything that happened before up until the event was created. Maybe I don't want to look at this because the source system is not under my control, so I cannot influence that, and therefore I don't want to track that. So instead I want a different definition of event time, of latency. I can, for example, say I want the processing delay. So in that, do I only want to include Flink? Do I want to include external systems as well? Well, that's up to you. You can also decide whether you want to exclude certain parts of your business logic. Maybe from the same argumentation, you could say, I exclude async IO, because that's not under my control. Also, your business logic can influence this event time lag. So if you have logic that is handling late events, then you're waiting for a certain amount of time, and you're waiting on purpose. So that's not negative from that point of view. So you decide whether you want to include that or not. The other thing that you might want to look at, a different definition of latency, is if you have some end-to-end exactly once sinks, then having something visible on the sinks depends on the checkpointing. So having that definition means you would include the time it takes to take a checkpoint and the frequency of the checkpoints as well. So you define that there are many more ways to define something. And what we've done in here is for low latency use cases, we defined our own event time lag. It's the same definition that we had before, that we had estimated before with built-in metrics, only this time it's more accurate. And then we can plot it. We use a histogram here, so we can plot the 99th percentile of this event time lag and then show this per operator, per subtask, or however you want to present it. Now, I'd like to walk you through this very small snippet of code to implement this metric. It's very useful to place in window functions or process functions like this. And you basically start by instantiating that metric. So here it's a histogram. So in the open method, I will get the runtime context, get the metric group that I want to append my metric to. And then in this case, it's a histogram called event time lag. And I use an implementation for a histogram that is offered by Flink. And then whenever I need it, I just update the metric. So in the process element, I look at the current processing time compared with a watermark, and then this is my metric. And this is all I need to do to get a histogram. Now it will be reported. It will be reported to whatever metrics reporter you have set up, so I can plot it in my dashboards. All right, so now, well, we looked at latency. There are also a couple of connector-specific metrics that indicate how far behind we are if we're looking at the head of a message queue. And these are metrics that come from external connectors. So for example, for Kafka, we could look at the record lag. So how far behind are we compared to what has been added to the start of the stream? Similarly, in Kinesis, you can see how many milliseconds you're behind. So those are metrics that come from your external systems, and you should monitor them as well. This mostly helps for debugging. If you want to know whether, for example, it's your Flink job which is slow to process, or whether just too many events stay inside the external source system, or maybe it's also the source that is slow in reading. That is one thing that you wouldn't see in backpressure. You would see that the source is busy all the time, so you got your indication there as well. But with those metrics combined from the external connectors, you get just more insight. Any performance monitoring that you do should come with throughput measurements. Even if you have a latency critical job and you're optimizing for latency, you do want to look at throughput. You do want to set up at least a benchmark where you look at throughput. But this is tracking, like say, any bottlenecks inside Flink as well. So you want to look at things like number of records in or out. You can look at those counters, like number of records in and out. You can also look at the rates, so per second. And then you can do alerting whether or when, for example, the number of records out is below a certain threshold. Now, number of records out is reported for all tasks in your Flink job except for syncs. Number of records in is similarly reported for all tasks in your Flink job or Flink application except for sources. The new Flip 27 and Flip 143 sources and syncs allow more metrics for sources and syncs as well. So those might track inputs at sources and outputs at syncs as well. But it's actually also enough if you track the throughputs, like the number of outgoing records out of your sources. Because if anything else further downstream, your Flink application is slow, then backpressure will make sure that this bubbles up upstream, up to your sources. So anything that is slow inside your job graph, wherever it is, it will come back to the sources. Similarly, you could also say you will see that the sync. You decide which one you want to monitor. In the end, the overall throughput of your application can be monitored at either sources or syncs, and you don't need to look at all the different operators or all the different tasks inside your application in order to track this. What you can do, however, if you look at specific tasks, that might help you in debugging. So you can track the throughput for specific subtasks or for specific operators, and then you identify bottlenecks as well. So this is where you may want to get more details. Now we've looked at throughput, we've looked at latency. Let's look at some more system level metrics. In that case, the JVM. And for continuous monitoring, or actually not just the JVM, we're looking at the Flink process that is running. And we can monitor this either through a couple of system metrics that Flink is forwarding, like the status JVM memory. And there are heap or non-heap and others where you can get details on. And there are also system level metrics that come from, for example, Kubernetes that you want to track. So for the continuous memory, for the continuous monitoring part, you do want to be informed if your memory limit is about to be hit. So for Kubernetes, you want to compare the current working set bytes with the memory limit bytes. And if that is above a certain threshold, then you might want to be alerted before your job is restarting. Similarly, you can also track this inside Flink, and you can track the heap or non-heap or meta space that is being used. If you want to be informed about things like class loader leaks, that would be the meta space to look out for, or a few other things that we'll go in a second. Now, this is useful for continuous monitoring. You should always have the memory in mind and in your alerts and dashboards. So we'll now switch over a bit to metrics which don't really make too much sense for continuous monitoring, but are very useful for troubleshooting. So we'll stay at those JVM or system level or process metrics, and we'll just extend on that. First, the job manager. So while we're looking at the job manager, we get the same number of metrics like JVM CPU, memory, or garbage collector that you might want to look at. And also system level metrics like memory, what we've been looking at before. Now the job manager is usually not too much interest because the load is typically low, except for cases where you have a high number of task managers to maintain. So if you have a single job manager, maybe just give it one CPU core and then have hundreds of task managers, that might just overload it. And you don't want to see timeouts on the RPC messages that job managers and task managers exchange. You want to act beforehand. So maybe this is even the continuous monitoring part with the CPU on the job manager. The load on the job manager can also be high if you have high checkpoint frequencies. So parts of the checkpoint handling are done inside the job manager, like orchestrating them and also inlining small checkpoint sizes. So if you configure the state storage memory threshold, then that means that small parts will not be checkpointed individually by the tasks, but rather sent to the job manager and assembled into the metadata file. So you don't have too many small files. And that is done by the job manager, and you need to leave room for doing that out of the job manager. And then specifically for application mode where user code is running at the job manager, you may have additional load that is happening there, but that's maybe a bit more rare than the others. Now let's get away from the job manager to the more interesting task managers. Same level of metrics, same key metrics to look at, different observations. So if you, well, first of all, you can keep track of the CPU, and you can also compare that with different task managers. If a single task manager is completely loaded and is slow, that will eventually be a bottleneck for the whole of your job graph, unless you have, like, say, very simple jobs without any network shuffles, without any connections between the task managers. Other than that, for troubleshooting, you don't usually need to alert on CPU because you're already monitoring throughput. So looking at CPU is useful for debugging, but not so much for alerting because throughput has a broader scope. You can look at load imbalances, you can look at problematic task managers. Also, we looked at this before, you should have your alerts on the memory. That's the same for task manager, so that they don't exceed their memory. Now I made a few special points for task managers that are based on, or that are using or running jobs using a heap-based state backend, and then also for RocksDB. So for heap-based state backends, you want to keep an eye on the memory that is being used, in particular the heap. So you can plot the different metrics that Flink offers, like heap, non-heap used, etc., and then look at that heap. If the heap is growing, then, well, it could just be that you have an increasing number of keys, so more state to store, which is perfectly fine, as long as you don't hit the memory limit. It could also mean that you have an event time skew between different input streams, that you're joining together. And if one stream is slow and not making progress as fast as the other, you might just have to buffer a lot inside Flink. It can also be an indicator of you failing to clean up stale state. So keep an eye on the heap and try to find out why it is increasing. And while we are at memory, for heap-based state backends, we're using heap, obviously, and that means garbage collection is running, and that can cause any problems from holding the system for some time, for example, and that increases latency. Flink forwards metrics like how often has garbage collection run, how long was it running. If you want more details, then you can enable JVM garbage collection logs and get more details in the logs. But that's more for debugging. Now for RocksDB. Unfortunately, Flink cannot completely control the memory RocksDB is using. So there's at least one part inside RocksDB that we're not controlling, and therefore you should still keep an eye out on memory that is being used versus memory that is available. And if you're getting too close to the memory limit, then you should adjust the framework size or the framework's off-heap memory or the JVM overhead, which would basically take memory away from the JVM, and therefore RocksDB's native memory has some additional space before you hit the limit. You should still keep an eye on the garbage collection, because other code that you're running could be using objects on the heap, while RocksDB itself is working off heap and then on disk. Now, while we're talking about RocksDB, there are a couple of key metrics to look at there as well. I'll just quickly walk through those, and we can then maybe go into the questions that came. There's a whole Flink documentation page telling you how to enable RocksDB metrics. Flink can forward those native metrics from RocksDB into Flink's metric system. However, you should carefully enable those because some might degrade performance. So I've chosen here the ones which don't influence performance or don't seem to influence performance much and are useful nonetheless. For example, the estimate live data size. With RocksDB, as you know, the size of the database on disk might not be what your actual data, might not be actual data size, because you might have stale data. So with that metric, you get an estimate of how much actual data you have. So you can compare it with the actual size on disk, and you can see that maybe you need to run compaction more often. Because if you only have, like in this job, let's say 800 megabytes of live data, but your on-disk structure is 5 gigabytes, then reads are probably degrading. Like the larger the ratio is, the more you have on disk versus what the actual state is, the more you have to read on every operation. You can track the background errors. I would say this is more of a debugging thing, because if there is any real error, then Flink would restart and you would see it from there. Performance-wise, you should keep an eye on the actual delayed write rate, which shows you or gives you an indication of write-heavy operations on potentially slow disks or things that you want to tune for writes. When we're writing things, then RocksDB, I mentioned we have potentially stale data on the disk. What RocksDB is doing is, in the background, it's having those compaction jobs, and there are a couple of metrics that monitor those compactions. So you can see how many bytes are waiting for compaction, how many compactions are running at the moment. So if you have lots of data that is waiting for compaction, maybe you want to increase compaction frequency, or you want to add more background jobs to do more compactions at the same time. And when you're writing things, when you have a write delay or have a write stopped, like from this metric, then you usually should look at flushes. So RocksDB is first writing into memory and then onto disk. And if this is stopped, if there are too many flushes running or pending, then you want to increase, disk throughput, or add more background jobs for flushing those parts to the disk. A few final words before we go to the Q&A. Well, we talked about monitoring a lot, but this shouldn't be the last step of your development before production. You should, or I recommend, that you start very early in your development by adding metrics, creating your own dashboards, and tracking the changes over time. They will also show you whenever you improve performance or whenever performance degrades. And you can get alerted on this before you go into production. There are a couple of other articles. There's a blog post on the Flink blog on monitoring Apache Flink applications 101. There's also a video on YouTube from Last Flink Forward from a colleague of mine, Alex Fedorov, about a debugger's guide to Apache Flink. So that one will walk you through further debugging tools that Flink has to offer. And last but not least, from this presentation, I'm actually currently writing a blog post which will give you all the details of the implementation, the dashboard, and everything I talked about, and that will be published soon on our website. So you can follow us either on our blog or on Twitter, and we will post it there. Now it's time for questions.
Thank you, Nico. So let's look at some questions. Well, the first one is, how is the impact on performance when using custom metrics?
That depends on the metric that you're using. So for the histograms that I've been using, for example, those are synchronized so that changing the data structure does not interrupt the metrics reporter, for example. So there's some overhead there. So if you see that it is problematic, and you can certainly do so with a profiler, then you can take any measures there. But I would say finding out what your application is doing is usually of higher interest than the last bits of performance here. In case you run into a problem, then you probably see the advantages of having those metrics. Otherwise, you wouldn't know what's happening underneath.
If the goal is to have solid and easy to put in place metrics solution, would you recommend InfluxDB, Prometheus, and Grafana as good tools?
We've been working with all of these. Like we've been doing for our training, we have a couple of exercises for troubleshooting and tuning, and we started working there with InfluxDB and then Grafana dashboard. Now we use Prometheus and also Grafana dashboard. You can also have Kibana dashboards. I don't think it makes much of a difference. So use the tool that you're comfortable with. But you can achieve the goals with all of those.
If we're using processing time rather than event time, does it make sense to use Flink's built-in latency metrics? How valuable are those? How can we interpret what they show us?
Yeah, Flink's built-in latency markers are, let's say, a bit difficult to handle. Like I see them more of a debugging tool. Like if you see that you have huge latency, then you enable them and you track where it is happening. On the other hand, they can also have some overhead on the runtime for maintaining. So it's maintaining the latency between every source and operator with different granularity. It's not directly measuring your business logic. So it's only measuring how long records are queued up in the buffers of Flink. It jumps business logic. So in that way, they're a bit difficult to interpret. And I would rather recommend having your own metrics if you want to measure latency. Because then you really know what you're measuring.
Thank you. I think that brings us to the end of the questions.
Thank you, everyone. If there are any more questions, feel free to still put them in.
Yes, one just showed up. Is it possible to have counters per key? Can we have per key metrics? I'd like to track how much data I'm dealing with on a per key basis so I can easily detect hotkeys.
I think that should be possible. However, if you have too many metrics, you might just overload Flink's metric system. And that will be the biggest concern that I have with this. So I'd rather log this out than keep this per key. I mean, if you know that your key space is limited, then I don't see a problem with it. You just initialize the counter the same way that I did in open, but I believe it should also work if you do that in the process function. But really, if you have too many metrics, like the Flink UI, for example, is fetching all metrics from the task managers. And if you just blow that up to too high value, those metrics are sent over akka, and there is the akka frame size limit that might prevent you from doing what you want to do. But for a limited and small key space.
Maybe one way to, I guess with a custom metric reporter, you could carefully only report the ones that are significantly large.
I think the web UI works outside of the metrics reporters, right? So that might still be affected. Unless you're not using the web UI, then it's not a problem. But that's a useful tool for debugging, especially from Flink 113 up.
Don't see any more questions.
I see just one more. Can we record metrics across jobs or aggregated across completed jobs? Like total data processed. I guess this is more of a thing to add to your dashboard.
This is somewhat related to a question that I answered in the chat, which was about, are metrics checkpointed? I already answered that they're not.
Yeah, but it should be relatively easy to track this inside your dashboard. You just say plot the, data processed for a bunch of jobs and then sum them up. All right, then if there are no more questions, I'd like to thank you for listening. And well, looking forward to publishing that blog post, and then you get more details, and you can take the dashboard that I want to share for a starting point to your own monitoring. Thanks, have a nice evening, have a nice day, and see you next time.